Hi, Evelyn. You're welcome to ask me questions if you have any. At least till class starts. Ew.
Hi, Professor. Can you hear
Hey,
me?
how you doing?
Yes. Good afternoon. I just have a quick question. For the in-person exams, would they be during our lab, or should we go ahead and schedule time with a proctor to take them?
We're probably not going to be able to use our lab, so yeah, definitely if you can schedule a time with the proctor, that'd be great.
Okay, sounds good.
No problem. Thank you. Ooh, got more people coming in. Looking good. More people. Another one coming in. All right. I got another one now. Right. Anybody have any questions before we get started? It is now time to begin, so we can crank her up in a second. Hmm. That seems like no. All right. I just want to remind you, you do have a test, an online test that's due Tuesday. Actually, it's technically due Monday night at 11:59 p.m. Normally, I think I even said it would be due Sunday at 11:59 p.m. But since you guys meet on Tuesdays and Thursdays, I went ahead and pushed that back to Wednesday, or excuse me, to Monday at 11:59 p.m. So make sure you don't forget to do that. Also, while you're here, go ahead and chat me your first and last name. I remind everybody, let me know if there's anything going on where I mean, you don't have to tell me any details whatsoever, but if any of y'all have reasons for not wanting your name, I can't imagine a scenario where your face would appear, but definitely not, definitely don't plan on putting your name on my YouTube channel unless, you know, you said or unless you told me it was okay. So if anybody has any problems with your name popping up, feel free to change the name to just like your first name and your first initial of your last name. That would be fine. But also, you know, let me know if you still have a problem with it so I can make sure I change that. I try to tell everybody at the very beginning, but I also every now and then want to reiterate it. I don't generally try to put your names on the internet at all, but sometimes like when we're waiting for people to come in, your name will appear first in the center of the screen for a brief second. I usually try to edit that out, but I haven't been able to keep up the rate of doing any editing yet. So just let me know if there's any reason, and then I'll make sure that your name doesn't appear. So, any questions now that I said all that stuff? How you doing, Hannah? You look like you're tired.
I'm doing good. I am tired today, but I'm going to lab tonight to make up
Gotcha.
last Tuesday's lab. So I gotta wake up.
I'm tired too. I had to come here. I got a flat on my way to work yesterday. It was actually already flat when I left, and I didn't know it because I have low profile tires, so it's hard to feel anything. But then it started making noise, and I was going to come home, just take it off real quick, take it over to a friend, get him to patch it. But I pulled it off, and it had a slit all the way around the inside. So I ended up with my bad shoulder. I had to pull a tire and take it off the rim, find a replacement tire, put it back on the rim, and put it back on the car. So I'm exhausted now. A whole 8 minutes of fat man work. All right, well, let's go ahead and get started. When we finished last time, we were in chapter 19, but we certainly weren't finished because chapter 19 covers so much material. But the important thing is we are moving along in it and we're doing okay, I guess. So let's keep that up. I'm going to start off with in the chapter, and I'd actually suggested you guys make sure you read exercise 19.7 and several other problems. But basically, remember the bare minimum of reading your book is at least skimming the paragraphs and then making sure you write down and commit to memory all of the italicized text and bold-faced text. I would say it's worthwhile doing that as a bare minimum, even in the sections that I don't cover. But then once you finish with that, make sure as you get to an example, make sure you read it and thoroughly understand it because you are really responsible for all the examples except in subsections where I tell you we're skipping. So this problem says a waiter puts a 0.754 chunk of ice at negative 12.5 degrees Celsius into 3.78 kilograms of tea at 20.0 degrees Celsius. At what temperature will the iced tea be? And that's supposed to say iced tea, not iced, and then without the word tea in there. So iced tea.
Did you mean to share your notes on the
Yeah,
screen?
yeah. Thank
Okay.
you. Uh, and yeah, I had forgot, so it's good that you told me anyways.
Yeah, I was trying to like write down the question. I'm like, oh, he lost me like 5 words ago.
Yeah, now I'm trying to find my Zoom window. That would be helpful too. Any little, oh, there you go. Ooh, found the button. Okay, cool. Oh, and another person came. All right. So yeah, let me go ahead and share my text, but this is the first example we're working, and you should see it on your screen momentarily. Thanks for reminding me, Hannah. We need that when we get old. We need young people to tell us, hey, you forgot to turn your computer on, or hey, you forgot your pants and you're going to work. All right, so that's the question. Now, the big thing with this is you really don't know what the results are. This is a calorimetry problem, but because you don't really necessarily know how much heat it takes to completely melt all the ice, uh, so you don't know if this is going to be an iced tea mixture. Ideally, iced tea is supposed to be at 0.0 degrees Celsius, so it's really, really ice cold, even though it's not necessarily ice. It could have solid chunks in it, or not, but the main thing is we've got to figure that out before we do the calculations. So what I'm going to do is I'm going to start off by trying to estimate how much energy has to be removed from the ice to bring it to 0 degrees Celsius, and then how much energy has to be removed from the ice to make it change state. And then I'm going to see how much energy it takes to actually raise the water, or excuse me, lower the water down to 0 degrees Celsius. And if that's not enough energy, then we know for a fact that it won't all melt. So that's what we got to check first. So the equations we'll need, of course, are Q is equal to MC delta T for changing the temperature of any substance. We also need Q is equal to M times L. In this case, we're talking heat of fusion because we're going to the solidification of ice as opposed to changing it from water to steam. We're going from changing it from solid to water, so it's fusion, not vaporization. And I also need the values that correspond to the heat of vaporization, or excuse me, the heat of fusion for ice, and the heat of fusion, or excuse me, and the specific heat of water. So I'm looking at the heat of fusion for ice, and this time I'm going to go ahead and use the kilojoules. So the heat of fusion for ice is heat of fusion L sub F is equal to 333 kilojoules per kilogram. And we also need the specific heat of water, which we know specific heat of water, because we're going to assume the T is actually water. Uh, Obviously, if you put a ton of sugar, it's not going to be anymore. So be careful with that estimation, or at least if you're taking some kind of test where someone's going to grade it for your competence in this field or whatever, then you want to make at least state verbally that you're going on the assumption that iced tea or tea itself is essentially the same thing as water, and that's the approximation you're using. The specific heat of water, and specifically in the liquid state, so I'll put an L on it, that should be 4,186 joules per kilogram. Okay, so that should do all we need. So first off, I'm going to see exactly how much energy it takes to bring the ice temperature up. So let's say ice to 0. The Q for ice to 0 is the mass of the ice, which is 0.754 kilograms. Oh yeah, I do need the specific heat of ice for solid too. So CH2O. If I remember correctly, that is 2100, and this time it'll be for a solid. Let me double check on that since I'm going off the top of my head. I think it's 2100 is what we ended up doing for ice, and steam is supposed to be like 20 or 2000 or something like that. So here I found the table. So ice, yes, ice is 2100, steam is 2010. So and that's 2100. Again, this would be, that was joules per kilogram Celsius degree. I left off a unit there. And this one would be joules per kilogram Celsius degree. Notice the units for specific heat are energy per mass Celsius degree, whereas the units for heat of vaporization, heat of fluid, heat of vapor fusion are just what we call latent heat, is just energy per kilogram or energy per gram, depending on what units you're using. So we've got all that now. So now I'm just going to go ahead and calculate this. The specific heat of ice would be 2100 joules per kilogram Celsius degree. And then the change in temperature would ultimately be the final temperature is 0. Oh man, I hate when my pad does that. Is 0.0 degrees Celsius minus the initial temperature, which is negative 12.5 degrees Celsius. And you can see that means we actually are going to get a positive amount of heat, because it actually takes a positive amount of heat to bring ice up in temperature, just like everything. So I've got my calculator on. 0.754 times 2100, which I'm assuming is 4 sig figs. So I'll put a dot right next to it, even though it's almost certainly only, maybe only 3 sig figs. Hopefully it's 3 sig figs, not 2. But anyways, that's going to be 0.754 times 2100 times 12.5. And that gives me 19,792, or approximately 19,793 joules. I'm going on the assumption that we have 3 sig figs, so the 9 and the 3, which actually was 92.5. But either way, the last 2 digits here are not significant figures. Now I need to figure out the heat required to actually change the state of ice. So I'll say the heat of or the heat for M. Well, I'll say melting, the heat of melting. So in this case, it's going to be 0.754 kilograms times the 333 kilojoules per kilogram. And then that's it. So if I multiply 333 times 0.754, that gives me 251.08 kilojoules. Now that was only 3 sig figs, so I underline that. And this, of course, would mean 251 times 10 to the third joules. So the total heat required to completely melt all the ice, which means you got to first bring it up to 0 degrees Celsius and then put in the heat of fusion. That total is plus 19793. Actually, hold on a second. I just realized I forgot to convert the kilojoules to joules before I added it. So rather than screw it all up, I want to retype it. All right. So now I've got basically 270,875. So this is going to be 270,875 joules is the total amount it takes. In the case of the melting, we had the 200,000 and then the 10,000s and then the 1,000s digit. So everything after that is actually not a sig fig. So I'll say these 875s is not a significant figure. Now what I want to do is realize, see how much energy is in 20 degrees Celsius of essentially water, since it's T. And if that number is actually bigger than this number, then the T has the capacity to completely melt the ice. So QT is going to be the mass of the actual T, which would be 3.78 kilograms, times the specific heat of water in this case, which is 4186. And that is joules per kilogram Celsius degree. And then the temperature change would be final minus initial is supposed to be 0.0 degrees minus 20.0 degrees Celsius. You see, this one's going to come out negative, but the main thing is if it's 270,000 or bigger joules, then it can actually turn the whole thing into liquid. So let's see what happens. 3.78 times 4186 times negative 20. So that gives me 3 sig figs, and the answer is going to be a negative. And it looks like I got 316,462 joules. Of course, I only have 3 sig figs, so the 4, the 6, and the 2 are not sig figs. But we can see that 316,000 is greater than 271,000. So this should be more than enough energy to completely melt the ice, which means the whole mixture should likely be liquid. Does that make sense to everyone? Okay, so since we have pure liquid, then we're able to actually calculate the final temperature just by putting this into an equation, which in this case is going to be Q lost equals Q gained. And I'll write right here. Okay. So the thing losing the heat obviously is the T, and the thing gaining the heat is going to be the ice that ultimately turns to water and then is brought up to some new temperature. So what I'm going to say is Q for the T is equal to Q for the ice. Okay. Now, when I use this method as opposed to the summation of the Q's equals 0, I just got to make sure each term is positive. So when I do the delta T, this is one of those rare instances where delta doesn't necessarily mean final minus initial. In this case, I'm going to do big temperature minus small temperature. So if I write out the T was this 3.78 kilograms. So 3.78 kilograms times the specific heat of T, which is 4,186 joules per kilogram Celsius degree. And then the temperature, we don't actually know. The final temperature is going to be lower than 20 degrees Celsius. And the initial temperature is 20 degrees Celsius. So we're going to have to do 20.0 degrees Celsius minus T final. That makes that one positive by putting it in that order. And now I'm going to set that equal to Q for the ice, which is going to be 0.754 kilograms. We know it's going to change the temperature. And of course, the specific heat of ice was 2100. And that's joules per kilogram Celsius degree. And of course, we also know that there's more than enough to bring it up to 0. So this temperature is going to be, the final temperature is going to be 0, which is higher than 12.5. So I'm going to do 0.0 degrees Celsius minus negative 12.5 degrees Celsius. And I also have to have the heat of fusion. So that's going to be 0.754 kilograms times 333. And that should be kilojoules. I'll say 333 times 10 to the third joules per kilogram. And then we also need, once the entire ice has changed the temperature from negative 12.5 to 0, and then completely supplied enough heat of fusion to break up the lattice, then we're going to have to continue bringing the temperature of the liquid water that was just ice to bring that up to the final temperature. So that final temperature, of course, will be larger than the 0 degrees Celsius. So that's going to be the first one in the delta T. So 0.754 kilograms. Now it's water, so we're back to 4186 joules per kilogram Celsius degree. And it's going to be T final minus 0.0 degrees Celsius. So now all we have to do is distribute all these numbers and then solve for T final. We've already worked on the units on these types of problems, so it shouldn't be any problem for me to leave off the units at this point. I'm going to say 3.78 times 4186 times 20. And that gives me 3.1646. And that one just happens to be the 4 and the 6 are not sig figs, but that's 3.1646 times 10 to the 5. And notice we've already multiplied joules per kilogram Celsius degree times kilograms and Celsius degree. So that's going to give us just plain joules. And then on the right-hand side, we got 0.754 times 2100 times positive 12.5. So again, we get 3 sig figs. So this is going to be 197. I'm going to call it 1.9792. Again, only 2 sig figs, so the 2 is not significant. And actually, that should be 93. My fault. Forgot to round it. And this is times 10 to the 5. And that's just joules like it was before in the previous term. Now I've got to get the 0.754 times 333 times 10 to the third. So remember last time I just used 333, but it came out in kilojoules. So this time I did 333 times 10 to the third to make up for the kilo, and it'll just come out with joules. So when I did that, 0.754 times, almost made a mistake. I typed in only 33 instead of 333. So times 10 to the third. This all gets me 2.5108 times 10 to the 5th again, joules. That takes care of the second term on the right. And then, I did forget a term on the left, by the way, everybody. I don't know why I skipped it, but remember, I've still got to multiply 3.78 times 4186 times negative TF, because that's how we're going to solve for TF. So that's kind of a boo-boo. But anyways, I've now got potentially two terms in the last term on the right. I've got a 0.754 times 4186 times TF, but the other term is times 0, so that's just going to be 0. So I only have one. So 0.754 times 4186. Notice that's just going to cancel out the kilograms in the bottom, so I'll get joules per Celsius degree times TF, and that's going to be 3.1562. And that's times 10 to the, that's just times 10 to the 3. And that will be, as I said, joules per Celsius degree times T final. Now on the left-hand side, I am going to put the term that I just blatantly neglected, which in this case is going to be 3.78 times 4186. And that's it. So this is going to be 1.5823 times 10 to the fourth. And that's also joules per Celsius degree times TF. So I'll put a parenthesis around it. And as you can tell, we've got all our sig figs worked out to the appropriate places, to the appropriate digits with the underline where they are. So if I take the TF that's on the left-hand side and bring it over to the right, then that'll make my coefficients of TF positive. And if I subtract the other two non-TF terms from the right and put an atom, subtract them from the left, then that should give me just a pure number on the left. So I'm going to start with that 3.1646 times 10 to the fifth. I'm going to subtract from that 1.9793 times 10 to the fifth. And I'm going to subtract from that 2.5108 times 10 to the fifth. And that gives me 1.3255 times 10 to the fifth. And it'll actually be negative over here. 1.3255 times 10 to the fifth joules. This fact that it's coming out negative is a little concerning, but if the other side comes out negative, it won't be a problem. If it came out negative, oops. Yeah, that's right, just joule. So what I took care of was this term. Let me change to blue. I've now taken care of this term, and this term. If the other side comes out negative, then that'll be fine. But if it doesn't, that means that some kind of calculation I did in the beginning was messed up, and this is actually trying to turn the water to a temperature below zero, which would mean it didn't have enough energy to actually melt the ice, despite what I calculated ahead of time. So there would be like a mistake or something. But let's check this out. So now I'm going to take the 3.1562. So 3.1562 times 10 to the third. And I am going to add to that, crap, move, crap, it is coming out negative. And I don't think I missed anything. T final minus 0 degrees. That was fine. 0 is that one. That was fine. Okay. So let me check my numbers. 3.1646 times 10 to the fifth. That's right. I had 1.9793 times 10 to the fifth. That's right. And I had 2.5108 times 10 to the fifth. So all that works well, and that did give me negative 132,000. And by the way, since all of those had times 10 to the fifth, that means the third and fourth decimal place were the non-significant digits. I meant to put that in red. So there that is, and there that is. Okay. So it does look like there was some kind of mistake. I'm looking back at it. I don't know how that would have been a problem, but there seems to have been one. So now I'm going to do 3.1562 times 10 to the third plus, so 3.1562 times 10 to the third plus 1.5823 times 10 to the fourth. And this is going to give me 18,979. So that gives me 18,979 9.7, and it's 9.2, so I'm just going to round that to 9, and that would be joules per Celsius degree times T final. And again, we only had 3 sig figs. That would have been the first two at 10 to the third, and this one was 10 to the fourth. It'd be, let me think of this real quick. 1.5823 times 10 to the fourth would be 15823, and the 2 and 3 are not. And then we also had the 31562, and that one was times 10 to the 3. So that would be right here. And the 6 and the 2 were not significant. So it appears that we can only go down to the hundreds place. So that means the 7 and the 9 in this one is not a sig fig. And technically, when I solve this for T final, I'm going to get a negative temperature, but we've got to basically regroup and see what's wrong with that. But what I did was right. It's just I probably made some kind of careless mistake. So what I'm going to do is take the 1.3255 times 10 to the fifth, and I'm going to divide it by 18979, and that's going to give me a temperature of negative, because I did divide by a negative, 6.9840 degrees Celsius. In this case, we divided 3 sig figs by 3 sig figs, so the 4 and the 0 is not sig figs. But what this tells us is that the ice took more energy to melt and to bring up to 0 degrees Celsius than it took for the tea to be getting rid of to get down from 20 degrees Celsius to 0. I'm going to check these numbers again. So when I did ice to 0, I did 0.754 kilograms. So what I'm looking at, just so everybody's on the same page, I'm looking at this number and this number to see if they're right, and then add them together and to see if they're bigger than this number. Because what I found out, or excuse me, was bigger than this number. What I had found out was this number was bigger. I got 316,000, and the other one was only like 270,000. So I thought it would take way less energy than it did. So let me check my numbers on QI to 0. Y'all can do this too. Has anybody done any of this yet? Did y'all calculate the same numbers and get the same answers I did?
I got the same because I just kind of did it along with you, and I got the same thing.
Gotcha. Okay. Well, that makes me feel a little better, meaning I didn't. So I did get 19,793 for this one. So I'm just going to put a little blue check mark by it to suggest that one is correct. And now I'm going to do 0.754, and I'm going to do that times 333 times 10 to the third, because it is kilojoules, and I can get rid of kilo that way. And hopefully this one comes out to be the right answer. That gives me, ooh, 251. No, that's right. This one gave me 25102, 082. So let me write it above it. I got 251,082 joules. And of course, I only had 3 sig figs, so these last 3 sig figs are not right. So I basically have 215,000 added to 19,000, and somehow I made a mistake in adding those two. Let's say plus 19792, or 793 since I rounded it. That gives me 270,875. So it does appear that this number is correct. And this number is correct. 875, yep. So now I'm going to check to make sure the QT is correct. And that is the kilograms was 3.78 and the temperature was 20. We're bringing it down to 0. So 3.78 times 4186 times 0 minus 20. So that'd be times 20. And that gives me 316,462 negative. So this answer looks correct as well. So I cannot imagine 3.78418620 is what I got on the left-hand side. That's for the T losing heat. And for the ice gaining heat, this number right here should be the exact same thing as this number. And then this number right here should be the exact same thing as this number right here. So let's check. I got 1.9793. That's times 10 to the 5th. So that checks with this guy. So I'll put a little X on it that I know that one's correct. And the 251,082 times 10 to the 5th. 251. The only difference is I didn't carry that extra 2 on this one, so that number seems fine. And the 316,462, that number's fine. The only thing I didn't carry was the 2 on the end. And that is times 10 to the 5th. Okay, so it looks like all those numbers are right. So when I subtracted the 316,000 minus the other 2, that should have gave me a positive number. Let's check and see if I did my math right there. So 316,462. 316,462. It's 61.6, so I'm just saying that. And then I'm going to say minus 19793. And then I'm going to say minus 251,082. Ah, there you go. So I must have made some mistake in this subtraction where I got the answer was negative 1.32. That's the part that's wrong. So right here, everybody, y'all see this number? That's the number I got wrong. Okay. So that number should have been instead. So I'm going to go ahead and erase it, everybody. So you're going to erase this number 2. I'm going to take this out right here. And now in its stead, of course, I'm also going to erase this because this temperature is no longer right. But in place of it, I'm going to write it in blue. So remember, it's 45,587. Joules. And what we had was basically this was good to the thousands place. The 3.16 was good to the thousands place. The 1.97 was as well, and the 2.51 was as well. So basically only the 5 and the 8 and the 7 were not significant, and that should have gave me just plain joules. So now I'll take that 45,587 and I'm going to divide it by 18979. Ah, that's much better. Okay, so the final answer is in fact 2.402. Again, carrying 2 extra sig fig, or in this case, I carried only 1 extra sig fig. So 2.40. I could go ahead and do 2. Yeah, I'll do that. 19. And that's degrees Celsius. So it does bring it really, really close to 0 degrees Celsius, but not quite. So everything we did was correct. I just clearly made some kind of mistake when I came up with a negative number. I might have done something stupid like just left off a digit, but that works out. Anybody have any questions on that one? Okay. Now your book does a problem just like this. Obviously the numbers are different, the wording's a little different, but the main thing is it does something just like this. And I will remind you that you don't have to do it in the Q loss equals Q gain way. Your book also teaches you the summation of the Q's is equal to 0, and that works fine. When you do that, the heat of vaporization, the heat of fusion, that term takes a little thought to realize whether that heat of vaporization or heat of fusion should be positive or negative. Obviously, if you remember the graph I made for 1 kilogram of water, you saw that in going from solid ice to water, the latent heat of fusion was a positive quantity. And then in going from liquid water to gas, the latent heat of vaporization was also a positive quantity. So just remember, as you're going up the temperature scale, the latent heats will be positive, and as you're going down the temperature scale, they should be negative. So that'll help you keep your signs right if you do choose to use the delta, the summation of the Q's equals 0. And then if you're using the summation of Q's equals 0, like I said, you have to do delta T properly, which would be T final minus T initial every time. Any questions on that? That took a lot longer than it was supposed to. So sorry about that, but luckily we didn't really make a mistake. We just thought we did, so that was kind of good. No questions on this? So notice when you're doing a calorimetry problem that involves a change of state, you don't necessarily know whether there's going to be enough energy to completely change the state of the thing whose state is changing. So you've got to first check the numbers before you actually set it up as a calorimetry problem. And that's what I did here. And everything, like I said, went pretty well until that very last step when I started trying to solve the equation. So just keep that in mind. Your book does have a problem solving box in chapter 19 that tells you how to go about solving it. I definitely recommend you read that so you'll make some sense of it. Let's go ahead and now consider, I'm going to leave you with example 19.8 in the book. I think that's really well done. It has a solution written out in sentence form, all that good stuff. So you can exactly see what they're doing. And I'll just, like I said, go on from here to the next section and start using the equations that I haven't used yet. So I'll leave example 19-8 for you to work out. Okay, that doesn't mean that you can't ask me. So if you have any problems with it, you don't think you understand how they got from step 1 to step 2, or from some line in the work to some other line in the work, that's what you're supposed to be figuring out on these examples. So if you can't, just take a picture of your work, take a picture of the question, and send them to me. You can send them to me by email, or you can send them to me by text, and I'll help you figure out whatever went wrong. Now we're going on from here to, your book talks about evaporation. In fact, I've highlighted a particular segment of the text where it says this process is called evaporation. That's the middle of the paragraph. It says the latent heat of change, latent heat to change a liquid to a gas is needed not only at the boiling point. Water can change from the liquid to the gas phase even at room temperature. This process is called evaporation. The value of heat of vaporization of water increases slightly with a decrease in temperature. At 20 degrees Celsius, for example, it is 2,450 kilojoules per kilogram compared to 2,260. So 2,450 versus 2,260 kilojoules per kilogram at 100 degrees Celsius. So you do actually have to use a slightly larger heat of vaporization for it to evaporate at a lower temperature, but still it can. And when water evaporates, the remaining liquid cools because the energy required, the latent heat of vaporization, comes from the water itself. So that whole sentence that I highlighted for you, which starts basically at that description of the 2450 and the 2260, that is basically the way sweating works. So when you release water onto the outsides of your skin by sweating, that water is it's mostly water, but it's also got salt and all sorts of stuff like that in it. But basically what happens is in the atmosphere, if it's not too humid, if it is too humid, then the air is virtually saturated, so it can't accept any more water, so it won't necessarily evaporate. That's the dangers of working out and doing too strenuous of stuff on too hot or too humid of days. But ignoring the humidity, if it can, the sweat on your skin will evaporate and it takes the heat from the water itself that's on your skin to make part of the water evaporate. And that water then cools down, and all of a sudden, the sweat on your skin is a colder temperature than the 98.6 that it came out at, and therefore it's cooling you off. Not only that, remember the heat of or the specific heat of water is so high it takes your body a lot of energy to bring that water temperature from whatever lower temperature it is up to 98.6. So it really is working to cool you. Anybody have any questions on that? So that section on evaporation was really largely a conceptual one for you to understand. And actually, it looks like I might not have the part that I highlighted doesn't look like I necessarily highlighted it in the way that I intended to. Huh, and it's not letting me do it now. That's weird. See this. Huh, okay. All right, well, it's not letting me change it here. I don't know why, but that's okay. So now I'm going on to the next section, which is 19-5-2, the kinetic theory of latent heats. It says we can make use of kinetic theory to see why energy is needed to melt or vaporize a substance. At the melting point, the latent heat of fusion does not act to increase the average kinetic energy and the temperature of the molecules of the solid, but instead is used to overcome the potential energy associated with the force between the molecules. That is, work must be done against the attractive forces to break the molecules loose from their relatively fixed positions in the solid so that they can freely roll over one another in the liquid phase. So you're actually, getting rid of a Coulomb potential energy to some extent. Similarly, energy is required for molecules held close together in the liquid phase to escape into the gaseous phase where they are far apart. The vaporization process is a more energetic reorganization of the molecules than is melting. The average distance between the molecules is greatly increased, and hence the vaporization is generally much greater than the heat of fusion for a given substance. So that's kind of neat. In fact, that's specifically a question that one of my students asked me about water. And I didn't know in general if this is a common property to all elements, but we did see there was a large difference in heat of vaporization versus heat of fusion for water. Water was like 79.7 for heat of fusion and 539 for heat of vaporization. So notice, 79.7 versus 539 is huge. The first law of thermodynamics is what we're covering now. So I'm going to go ahead and write the first law of thermodynamics. I think I might have given you this previously. I just made that E, which I don't know how E came out of my hands anyways, but I made that E into an S. So it's first law of thermodynamics. And basically the way we do it in physics, and specifically in this textbook, we use E internal for the internal energy instead of U. Most books I'm familiar with use U for the internal energy. We're using E sub I and T. And I know that curvy E line makes it look a little weird, but it is just a regular E. Okay. And if you're excluding mechanical energy, then that's equal to the heat added, that's what Q is, minus the work done by the substance. So work one more work done by the system, meaning the system you're studying. And this one's going to be the heat added to the system. Okay. Because of that, because we're calculating the work done by the system, which is weird compared to what you're used to in chemistry, but because of that, it's minus W instead of plus W. So if you're taking chemistry, you'll probably get the first law of thermodynamics written like this. They probably use U too, but it might say something like delta U is equal to Q plus W. Because in chemistry, they're wondering how much energy goes into the actual chemicals that are doing the work. So the work done to the chemicals is what's relevant to them. Whereas in physics, we were doing this to figure out how much work is put out by, for instance, a steam engine or something like that. So our interest was more in the actual work produced. So that's why we use that W and they use the other W. Okay. Any questions on that? Now, it is, as I told you, basically a statement of conservation of energy. So if you wanted to generalize it to include mechanical energy, you'd say plus delta kinetic energy plus delta U potential energy. So that's the generalized first law of thermodynamics. Remember when we did conservation mechanical energy, one of the ways you could have done it was delta U plus delta K is equal to 0. And you can see how that works because we weren't taking into account heat being added to the system or work being done by the system. But the way I did it in my, if you had me for 241, was I did all the initial energies is equal to all the final energies. And I even had a work in and work out term. So that was already somewhat consistent with the first law of thermodynamics that we're learning here. So anybody have any questions on that? You'll notice there's some italics and boldface print in this section, 19-6. So make sure you read those because really what I was telling you by writing work done by the system and heat added to the system was the sign convention. So you've got to sort of make use of that. So let's go on to talking about some other things. They said specifically for your sign conventions, heat is added, that means Q is positive. Heat is lost, that means Q is negative. Work done on the system, that means the work is negative, and work done by the system, that means the work is positive. They say it's known as the law of conservation of energy, and they say that it applies to a closed system. It also applies to an open system if we take into account the change in internal energy due to the increase or decrease in the amount of matter. And they give you some other things like they start talking about state variables. So quantities which describe the state of a system, such as internal energy, pressure, volume, temperature, mass, or number of moles, are referred to as state variables. And then equations like van der Waals equation and the ideal gas law, they're what we call equations of state. Your book defines what it means by changes and by thermodynamic processes. and state variables and state equations and so on and so forth. So that's again why you want to read the chapter and commit to memory the italics and boldface stuff. It does say caution, pressure, volume, temperature, internal energy, mass, and number of moles are state variables. W and Q are not. Okay, so that's a key thing because sometimes we will write the first law of thermodynamics in a slightly different way. We might write it as D E internal, so we could examine a very small change in internal energy, and in specifically what we would call a differential amount. That's why it's using a D. But in so doing, we would be tempted to write dq minus dw, but that's not acceptable because q and w are not state variables. So we have to put that little slash on it. That's the way I write it when I want to do that. Because in that case, I literally mean dq is a small amount of heat added and dw is a small amount of work done. It's not a differential, meaning I can't integrate that d bar w or that d bar q and get a w as an equation of state, nor can I get a q of it as an equation of state. So that's what that whole caution is about. Anybody have any questions on that? All right, so a simple example for the first law of thermodynamics is going to be right here. This will be example, I think this is 3, ain't it, or is this 2? Nope, it was example 2. Man, that last one really took a long time. So example 2, I'm going to imagine 3,000. Notice I put my decimal point there. I could have just said 3.000 times 10 to the third, but you see why I don't do that. But 3,000 joules of heat is added to a system. I'll say to the system. And 2,200 joules of work is done on the system. What is the change in internal energy? My G just got out of hand there. What is the change in internal energy? And that's supposed to be a Y that turned into a G as well. Okay, solution. So the relevant equation is obviously delta E internal is equal to Q minus W, but of course with that comes the sign convention. So what we can say is delta E internal is equal to Q is supposed to be the heat added to the system, and this says 3,000 joules of heat is added to the system, so we know that's a positive amount. So I'm going to write positive 3.000 times 10 to the third joules, and then minus W is supposed to be work done by the system, but it says and 2,200 joules of work is done on the system. So I'm going to underline this right here to let you all realize that this is a negative amount of work done. So I'm going to say negative 2.200 times 10 to the third joules. That way I don't have to write my little underbars and random dots and that sort of thing. So basically what we're going to get is 5,200, which I'll call 5.200 times 10 to the third joules. Any questions on that? So that's the answer for that one. Not too hard. That's pretty straightforward use of the first law of thermodynamics. Anybody have any questions? Now you can look at, and I'm going to leave this one for you because it's really pretty straightforward. But you can look at the generalized form and an example of it in example 19-10. So I'm just going to say C. Whoa. Let's say C. Yeah, darn it. 19-10. So that's one where they're actually making use of the full version of the conservation of energy, specifically the delta K plus the delta U plus the delta E internal equals Q minus W. So it's a fairly straightforward application. It's really straightforward, and it looks a lot like what we would have done in 241. So I didn't want to spend any time doing that. I want to get on to the new terminology and stuff that we need, because the rest of this is about basically some thermodynamic processes. So section 19.7 starts with thermodynamic processes and the first law, and I'm going to give you a rundown of what they are. So for instance, we first have an isothermal process. So I'll say isothermal. So we're talking processes in general. That's mainly means anything you can do to change the system you're studying. This one happens to be isothermal, and isothermal means that the change in temperature is zero. Okay. Since the change in temperature is zero, we can make certain conclusions. For instance, we can say PV equals nRT. Tells us that, for instance, PV over N is equal to a constant. And most of the time it's a closed system, which means the mass or the molecules or the atoms can't change, in which case you wouldn't even have the N down there. So you could say P1 V1 over N1 is equal to P2 V2 over N2. But like I said, in most cases, it'd just be P1 V1 is equal to P2 V2. So again, that's for ideal gases. And mainly is if you have the conditions that are right for a gas to behave like an ideal gas, then that's how the actual gas is going to behave. So that's what an isothermal process is. So if the isothermal process, for instance, is on an ideal gas, we've already learned that the potential energy, or excuse me, the internal energy is delta is E internal is equal to N times 3/2 kT for a monatomic ideal gas. And that tells you that temperature is the only thing that the internal energy depends on. So also for an ideal gas, ideal monatomic gas, that also means that E internal is equal to 3/2 N times K times T, which could also be 3/2 N times R times T. Okay. But notice, since it's isothermal, T can't change. Therefore, delta E internal is equal to 0, and we reach the conclusion that Q is equal to W. So this is a really big deal. We've got a statement about what happens to the first law of thermodynamics in a isothermal process. It's going to talk about PV diagrams and stuff like that, which the chapter's already been talking about. It'll talk about a heat reservoir. You can imagine a heat reservoir as anything that you can put in thermal contact with your system such that your system can release heat or steal heat as much as it wants. And then that thing that you've got in contact with your system is not going to change temperature. That's what a heat reservoir is. So you can imagine a giant lake, for instance, and if your system happens to be a little beaker of water that's floating in the lake, then obviously any kind of heat that the beaker of liquid is producing or taking away is not going to make a difference to the total temperature of the lake. So that's why the lake would be considered a heat reservoir. There's processes like compression, expansion, all sorts of other processes too, but we can classify them as quasi-static if they go very, very slowly. So what we're imagining is basically it's a bunch of equilibrium states between the initial state and the final state, and it just goes really slow from one equilibrium state to another, to another, to another, to another, to another, until we get to the end. When we do that, that's called a quasi-static state. And that's something that's important because when you actually do something a quasi-static state, then you always are going through equilibrium positions, and therefore you can actually make a graph. Notice a P versus V diagram or a P versus T diagram. Those are non-existent if the pressure, volume, temperature never reaches an equilibrium. So you couldn't even make the graphs if it wasn't a quasi-static process, because you literally only can graph the position, pressure, volume, temperature. You can only plot those in a graph if you're at an equilibrium state. Let's go on further. I will say for an ideal gas, something you might also want to know is on a pressure versus volume graph, an isotherm looks like this, and then another isotherm looks like this. And you can tell that's the case because PV over N is equal to a constant. And in that case, they're just saying P times V equals a constant. So that's what we call a hyperbola. But basically what it is P is equal to a constant over V. But the important thing about that is this isotherm corresponds to high T, and this one corresponds to a lower temperature. So keep that in mind when you're looking at plots of pressure versus volume. If you have an isotherm, the one that's higher, in other words, the one that has the higher pressure for a given volume, is the one with the higher temperature. And you can tell that from the ideal gas law because P times V is equal to N times R times T. Any questions on that? So that's one process. That's an isothermal process. And as I said, the big thing that we discovered, at least for an ideal gas, is that we got Q is equal to W in that scenario. I can also simplify this. Instead of just saying internal energy is equal to 3/2, I can say delta internal energy is equal to 3/2 N K delta T, which equals 3/2 lowercase n r delta T. So all of that stuff is important stuff that you'll need. Again, it's for an ideal monatomic gas that's true. We only got about 11 more minutes. The next process we want to talk about is an adiabatic process. And again, I use that nice little drawing tool where it makes my line straight, but if I don't turn it off, then it messes up my writing. So an adiabatic process is one where you're not allowed to add or take away any heat. So adiabatic implies Q is equal to 0. And of course, that means delta E internal is only equal to the negative of the work done. So that's another conclusion we can reach. And that's kind of helpful. But it turns out, and your book does a variation on this, a derivation of it too. But now you can make a plot of pressure versus temperature, or pressure versus volume, excuse me. So pressure versus volume, and you'll have one, let's say we have a state starting from this point right here. If you wanted to draw an isotherm, then it would be that hyperbola that we talked about. So this is an isotherm. But we could also follow an adiabat, in which case it leaves from that same point and would come down like this, and that would be an adiabat. Okay, so that's a line during which a process is is actually occurring, but it's occurring such that Q does not or that Q is equal to 0. So the big thing that you're figuring out there is the isotherm would be at a higher pressure at each state, at each volume than the adiabat. Any questions on that one? And you, of course, if you're dealing with an ideal monatomic gas, you can still do your 3/2 nRT or your 3/2 K NKT, that kind of stuff. Let's see. Another process is isobaric. So I'll draw a line to separate this. And now I'm going to see isobaric. That is a process for which y'all probably can tell delta P is equal to 0. So that means from PV equals nRT, you can basically say that V over NT is equal to a constant. And again, most times you have a closed system, in which case the N is a constant too, so you wouldn't have that. But in this case, you get V1 over N1 T1 is equal to V2 over N2 T2. Or more often is the case that it is a closed system, so you don't need to include that. So you could say V1 over T1 equals V2 over T2. But don't forget, your temperature's always got to be in Kelvin. You can't skip that part. Okay. And if you made a plot of pressure versus volume for this, there's your volume, there's your pressure, then an isobar would be that. Because clearly the pressure didn't change. Another process that we're going to study is called isovolumetric or isochoric. So let me separate that out again. And say isovolumetric, also called isochoric, if I remember correctly. Yeah, I might want to double check on that. That's the way I've always remembered it, but isochore always confused me, like it might actually be constant pressure, but I'll just put a little question mark over it just to be sure. But what this means, of course, is delta V is equal to 0, and then from PV equals nRT, what we have is P over NT is equal to a constant. So we could have P1 over N1 T1 is equal to P2 over N2 T2, or like I said, normally it's a closed system, so you just say P1 over T1 is equal to P2 over T2. But another thing that's pretty consequential for this is that since work equals the integral of F dot dl, which I learned last semester, and we say that force is equal to pressure times area, And if we are talking about pressures, then pressures are normally perpendicular to a surface, so that combining these two, we get work is equal to the integral of P dV. So delta V equals 0 implies work is equal to 0. And that means our second law of thermodynamics becomes delta E internal is just equal to Q. Okay, so that's another long drawn out process that can come to fruition. I will tell you also that in an adiabatic process, we learned that P1, V1 P1 V1 to the gamma power is equal to P2 V2 to the gamma power. So you can use that in addition to P1 V1 over T1 is equal to P2 V2 over T2, or P1 V1 equals P2 V2, all that stuff. The only thing is, of course, you've got to know what the gamma is, and your book does define that in the derivation process. And the gamma is supposed to be Cp over Cv, which is the specific heat at constant pressure divided by the specific heat at constant volume. And I was just verifying to make sure I remembered it correctly. So gamma is defined to be capital C P over capital V. So capital P is the one that says C with a P on it. That is the specific heat at constant pressure. And then the other one's the specific heat at constant volume. So let me tell you why they're different from a physical standpoint. We only got 3 minutes left, so this is a big concept that you need to understand. Your book does the derivation. You can find numerous examples of me doing the derivation on my YouTube channel, so check that out. But basically, when you put in heat to a system, you know from the first law of thermodynamics that heat can go into increasing the internal energy, but it could also go into feeding work. So it could actually make work. Like you could heat up a piston of air, and instead of that air just changing temperature inside the piston, it might change temperature a little bit, but not as much as you expect. And the reason is because some of the work, some of the heat went into expanding the volume of the piston. So for instance, you had that cylinder in there, and with the piston head sitting on top of it, you had a very fixed volume. But if you add heat, then the pressure is going to increase in size inside, and that's going to cause the piston to actually raise up. So you've got a little bit of heat that went to work, and the rest of the heat went to temperature. So that's why you'd expect CV to actually be, since it has the ability to do work, it could actually be quite a bit larger than or quite a bit smaller than the CV could. Whereas CV is, or excuse me, than the CP could. So the CP is a bit larger. And the reason why that's the case is basically when you add heat to the system at constant pressure, it can still do work, whereas the other one, it couldn't do work. Does that make sense? Because work is requires a change in volume by work equals integral PdV. So hopefully that helps you. Your book has a table in table 19.4 of those specific heats. We have yet again not finished chapter 19. I may make a video to finish off this chapter and just let y'all know about it, and then I'll take questions on Tuesday. But either way, I'm pushing the chapter 19 homework so that it's not due until Wednesday, or excuse me, until Wednesday night, 11:59 for you guys. Okay. All right. You guys are free to go. And once the last person leaves, and I'll split. You guys have a good, safe weekend, and let me know if I can do anything to help you. Do not forget to do your online test, please. Don't forget to type your name in if you haven't already. I think everybody did. Did you have a question, Hannah?
Yes, it's more of a technical difficulty problem.
Okay.
I was able to use my subscription from Physics 1 from last semester,
Right.
and it just, I guess, ran out. I thought I
Oh,
had bought it for the year, but I guess I'd only bought it for a certain amount of weeks,
gotcha.
and I cannot get back in there. So I was getting ready to purchase a like new thing for the semester, but I'm worried it's gonna put me in a new.
It shouldn't, but if you
Okay.
need any help with that, I would just call Pearson's technical service. You might even be able to purchase it over the phone with them, which would more than likely be considerably cheaper, or on the internet, either one, which would more than likely be considerably cheaper than buying it through our bookstore. But yeah, I would expect that because we did sell a cheaper version that was like 18 weeks or something like that, which is just bigger than a semester, but not as big as 2 semesters.
Yeah. Okay. But you like on your end, you can see all like the homeworks I've completed and
Yeah,
submitted.
it never erases it. Even if you completely drop the class, I'll have that, and literally a year later, it'll still show your work in there.
Perfect. Okay. Okay, then I will go ahead and I just want to make sure that everything was saved on your end so I don't have to restart. We haven't had that many homeworks due anyways, I don't think. Um,
Yeah,
there's not many odds.
yeah, we've only had two plus the intro and the primer. So yeah, you're golden. But yeah, when you go in, like if you, what you need to do is once you buy it, or once you're ready to buy it, go in and click on Access Pearson, click on one of the assignments that's listed in Canvas, and it'll take you to the Pearson site. At that time, it's supposed to tell you your trial or your period is run up, and it give you an access code or a place to put in an access code. When you put that in, it'll just automatically put you right back in the same account.
In the same. Awesome.
Okay.
Okay.
All right.
All,
Good luck. Sorry that happened to you.
all good. I just wanted to make sure before I didn't want to mess anything up. Alrighty.
Wait, don't you live? Actually, hold on a second before I say that. I'm going to stop sharing my screen, and I'm going to. You still there, Hannah? Sound like I heard you sneeze. Well, I tell you what, you have my number through my syllabus. So if you need anything else, just send me a text or give me a call or something like that. Uh, Otherwise, I'm going to go ahead and split out because one of us are clearly locked up due to our internet. Have a good one.